Well, I'm back to continue our discussion about gases. I'll give you a few seconds to copy down the notes here. Okay, and here is the problem we're going to work on, so copy that down as well. Well, we are into the gas laws, and so far we've talked about kinetic molecular theory, that description of gases. We've talked about some physical properties of gases. We talked about pressure and the relationships between pressure, volume, and temperature, and we're continuing that discussion because last time we talked about Boyle's law, which was the relationship between pressure and volume, and we said that that is an inverse relationship, that if pressure goes up, volume goes down, and if volume goes up, pressure goes down. And we saw that with a syringe. And you also watched the demonstration videos with that. Now, today we're going to talk about the observations of two Frenchmen and the laws that they observed involving first temperature and volume with Charles, and then with temperature and pressure for Gay-Lussac. So first, you watched some demonstration videos already for Charles' law, and so I want to incorporate those into our discussion. And what you observed in the first video was that as the balloon was heated up, so temperature went up, the balloon got larger, its volume increased. The reason for this is as temperature goes up, according to kinetic molecular theory, the molecules start to move faster. When they move faster, they want to get farther apart from one another, and so the volume will increase in a stretchy material like a balloon to equalize the pressure inside and outside of the balloon so that our pressure stays constant. In the second video, you watched a gentleman pour liquid nitrogen on the balloon, which lowered the temperature of the balloon. When you lower the temperature, the volume goes down. And so in a stretchy material like a balloon, the balloon shrinks to equalize that pressure inside and out. And then you saw as the balloon warmed up, the volume increased again. So that's what was going on. So if we take a look at the definition for Charles' law, it is when the pressure on a volume of dry gas is held constant, the Kelvin temperature and the volume are directly related. We are going to be working with Kelvin temperature. So if we are given our temperatures in degrees Celsius, we're going to have to convert, which we'll talk about later. I will remind you of how we do that. Now, Charles, he worked with hot air balloons. He actually, your textbook talks about this. He flew a hot air balloon, filled it with hydrogen, flew it, and this balloon, he landed in a field, and the farmers actually were very superstitious and afraid of the balloon, so they destroyed his balloon, which is kind of ironic that he was working on these things. But he was working with gases, and so he observed this, that when temperature increases, volume increases, and when temperature decreases, volume decreases. And so this is what the graph for that looks like. And this is a direct relationship graph. When one goes up, the other goes up. So mathematically, we can say that volume over temperature equals a constant. Let's say that constant is 1, hypothetically, just to see how this works. So if this is 1, volume and temperature, the numbers are the same. So 1 over 1 to start out with equals 1. Well, what if we increase the volume to 2? That means temperature has to increase to 2 to still equal 1. And if we increase the volume to 3, temperature has to increase to 3 to keep that value of 1. That's how this relationship works. Now, because in all those cases, no matter what, the constant is still the same, 1, we can say that if we have an initial volume and temperature, knowing that constant, we can relate it to a second volume and temperature of that same gas. And so we can get rid of K and just say V1 over T1 equals V2 over T2. So just like yesterday, let's take a look at how this works out mathematically with a problem. So our problem is a sample of gas occupies 430 milliliters when it is at a temperature of 25 degrees Celsius. What volume will it occupy when it is at standard temperature? Okay, let's identify what we have for all of our variables. And we're going to be using this equation up here, V1 over T1 equals V2 over T2. So, just trying to find my correct problem here. Okay. So, V1 and T1. V1 is 430 milliliters. T1 is 25 degrees Celsius. But up at the top I said that it has to be in Kelvin. So remember we add 273 to our Celsius temperatures to get Kelvin. And so 25 plus 273 is 298 Kelvin. V2 is what we're looking for, and they tell us that it's standard temperature. Remember from our discussion about STP, standard temperature and pressure from yesterday, the standard temperature is 273 K. 273 K, which is 0 degrees Celsius. So we plug these into our equation. V1 over T1 equals V2 over T2. 430 milliliters over 298 Kelvin is V2 over 273 Kelvin. We want to get V2 by itself, so we have to multiply both sides by 273 Kelvin. I'm going to go up over here to do that. So 430 milliliters over 298K times 273 Kelvin equals V2 over 273 Kelvin times 273 Kelvin. That cancels. So V2 equals, let's see, 430 times 273. Whoops. Is 117,390 divided by 298 equals 394 milliliters. Now, going back here though, this number is only 2 significant digits, so I have to round that off to 390 milliliters so that I only have 2 significant digits. This 0 is not significant because there's no decimal place after it. So that is how to do a Charles law problem. I'm going to stop the video here because I want you to watch some demonstration videos for the next law before I talk about it.